Okay, we're going to look at conditional probability now formally, and conditional probability is really, really interesting, and it's going to take some time to really digest. And so we're going to start off our conversation about conditional probability by just really building on some sort of basic structures of limits on probability and some definitions. So first of all, let's say that A is an event. So A is some event happening. Well, if A is some event, what we could do is say that the probability that A occurs, well, what must be true about that? What must be true about the probability that A occurs? Well, it can't be any more than 1. Because this is saying if it equaled 1, that would mean it happens 100% of the time. And so clearly, it can't happen more than 100% of the time. But it also must be greater than or equal to 0. And, using the same line of thinking, the probability of A, if it equaled 0, that would mean that it never happens. Okay, well, how about some notation? If A is an event happening, A prime, I say prime, but A, this line up here. So A prime means event A does not happen. So A is the event A happening. A prime is event A not happening. So what must be true about the probability of A happening added to the probability of A not happening? Pause the video here and think if you can answer. What must this sum be? Well, of course, these must add to 1, which is to say A can either happen or not happen. Something needs to happen. Either it does happen or it doesn't happen 100% of the time. Okay, so we get this idea then that the probability of A not happening is just 1 minus the probability of A happening. So this is a big idea. Let's look at some other ideas. Let's say that, imagine a tree diagram. We've got A happening and A not happening. And we've got the probability of A to get to A happening, and there's a likelihood of A not happening to get to A not happening. But let's think about some other event B. So let's say that event B depends on A. So this is dependent. It's a dependent event. So if A happens, then B could either happen or B could not happen. And if A doesn't happen, B could either happen or B could not happen. And what we're saying here, or what we could say is that, the probability that B happens depends on whether A has happened or not. So these values in here might not necessarily be the same. Let's look at this with some specific examples. Let's say that A is the event that it's sunny. And therefore A prime, well, that would just be not sunny. It's just the opposite of A. And let's define B as an event where you eat ice cream. So B prime is just the opposite. Do not eat ice cream. Okay, using this idea, what we could do is we could say, let's just create some potential probabilities. So the probability that it's sunny, let's say it's 0.8, which means that 80% of the time it's sunny. And the probability that it's not sunny, so A prime, well, it's just 1 minus that. And so it makes sense, that if we added these up, the probability that it's sunny and the probability that it's not sunny would be 1, which means that 100% of the time it's either sunny or not sunny. Okay, now let's say the probability that you eat ice cream, given that, so this straight line down means given that it's sunny. So what does this mean? This is saying, let's make an arrow. This is the probability of eating ice cream if it is sunny. And this is different from the probability of eating ice cream if it is not sunny. So this is notation to recognize that the probability of eating ice cream, depends on whether it was sunny or not sunny. Well, let's give some values to these. So we've got A being that it's sunny, and B, we've got eating ice cream. And what we're saying is that there is a 0.8 probability that it is sunny, and a 0.2 probability that it is not sunny. Now, if it is sunny, it could also be, or you could eat ice cream. And if it's sunny, you could also choose not to eat ice cream. So let's say that the probability here that you eat ice cream, given that it's sunny, let's say is 0.9. Whereas the probability that you don't eat ice cream, given that it's sunny, well, it has to be 0.1. Because you either, if we know that it's sunny, if it's sunny, we're either going to eat ice cream or we're going to not eat ice cream. So these two values need to add to 1. Okay, similarly, if it's not sunny, you could still eat ice cream or you could not eat ice cream. So the probability that you eat ice cream, given that it's not sunny, well, if it's not sunny, you're probably not going to want to eat ice cream as much. So maybe this is just 0.3. Whereas the probability that you don't eat ice cream, given that it's not sunny, well, it needs to, this number and this number need to add to 1. So this would be 0.7. So an interesting question then would be, find the probability that you eat ice cream. Interesting question. Why? Well, because there are a couple different ways for us to eat ice cream. We could either, let's see, for us to eat ice cream, we could either go on this path where it's sunny and we eat ice cream. So that's one way for us to eat ice cream. Or it could be not sunny and we could eat ice cream. So for us to eat ice cream, there are two ways. One is that it's sunny and then we eat ice cream. So that would be the probability of it being sunny multiplied by the probability that if it's sunny, we eat ice cream. So we're going to add that to the other way in which we could eat ice cream, which is if it's not sunny, so the probability of 0.2, times the probability that if it's not sunny, we still eat ice cream, which is 0.3. So summing those up, the net probability would be 0.72 plus 0.06, which equals 0.78. So this is an example of conditional probability. So let's generalize this just a little bit. If I have A and event B depends on A, and then not A, and my respective events, and we could have B not happening. So if we think about, just to generalize this, the probability of B happening, the way that we could write that is the probability of A joint B happening. So that's the probability of A and B happening. Union, so joined with the probability of A not happening, joined with B happening. And then to write that in terms of multiplication and addition, this is just the probability of A times the probability of, sorry, that should be a P, the probability of B given A plus the probability of not A times the probability of B given not A. So this is a big idea, and it's interesting, and it's kind of rich with some other important theorems, but for now let's stop here.